Because anything that, I really want you guys to know everything's on PowerPoint. And so anything we don't get over today, I mean, we'll continue on Wednesday, but it's still viable to be on the exam for Wednesday night, 7 p.m., 6 o'clock Central. Okay. So, all right. We were talking about mirroring dynamics. I'm just gonna go through this first 3 or 4 slides really quickly, just because of the fact that just to get you in the right frame of mind. The movement of lipids when it's laterally is really fast, just because of the fact that they can squirm around all over the place, and so very, very, very fast. If you're trying to flip it from the outer leaflet to the inner leaflet, or vice versa, it's much more slow unless it's catalyzed somehow. Okay? If it's going against the gradient, then it's going to require ATP. Okay? And so the two possibilities are flipases and flopases. Flipases go from the outside to the inside, and they only do the aminophospholipid, which we'll talk about in just a moment. And flopases only go from the inside to the outside. Okay, they do the other phospholipids. But once again, those all require ATP because they're going against the gradient. And then we have my favorite, scramblase, which sounds like scramblades. Okay, and it moves lipids in either direction, and it's to achieve the equilibrium, and so therefore it does not require additional energy from ATP, hydrolysis of ATP to ATP. Okay. All right. So, and I don't think I actually pointed this out before. I can't remember if I did or not. But its activity actually increases as a function of calcium. And calcium can go off for a whole host of things, but it does include apoptosis. The reason why I point that out is because one of the mechanisms of apoptosis is due to phosphatidylserine. So flipase helps combat that. And so by keeping the PS, the phosphatidylserine, from being on the outside of the plasma membrane too much. Okay, keep that concentration down. Help keep the asymmetric values up, so that way your cell stays around longer. Okay. So that's where we left off. Now we're going to talk a little bit about microdomains. Those that were in neurochemistry, we've talked a lot about microdomains and rafts. Okay. These, whenever I first started teaching here and teaching this class here, they didn't know a lot about rafts. They just knew they existed. But in the last 12 years, they found out that they're very, very, very important. What happened was they noticed, oh, whoops, my computer fell asleep again. They noticed that there were certain, I think it was first done on electron micrographs, but they noticed that there were certain regions of the membrane where it just seemed like certain lipids and proteins came together. And it kind of looked like little islands. I also heard them referred to as islands, islands in that sea of, but raft stuck around better than island, I guess. Okay, that's not the right. Let me bring up the correct class. Oh, while I'm doing that, because I just see the papers. The papers are not going to be due until the end of the day of the Thursday of finals week. What? Oh, okay. I thought you said something else. I was going to say no need to do that. But also one thing that I wanted to point out was make sure that you had, because a lot of people didn't have like an abstract or a detailed conclusion discussion section, and you'll want to do that. And also, I did point this out in multiple times, is that the mechanism, I am looking for an electron pushing kind of mechanism where you're talking about like the nucleophiles and electrophiles and things like that. Okay, why is this not wanting to come up? That's okay. So they called these rafts because they float together on this lipid membrane sea. I guess scientists can also wax poetical, occasionally at least. No, whoops, I went too far. So then I always put in this little picture, and if we have enough time, at the end of today or on Wednesday, I think I'll actually bring in a real life example of the importance of these that we did cover in neurochemistry, plus neurochemistry as well. So B is an artificial membrane to show you, I mean, they're using atomic force microscopy, which we're not going into details there, but you can see where there are certain lipids and proteins that kind of accumulate together, okay? And they associate together. Since this time, what they've noticed is many times, based off of what lipids and or proteins that are in that raft together, those rafts can have different functions. Or that's one way to activate something. In particular, especially when we talk about these cell signaling cascades, which we're going to start on next semester. So don't forget about this chapter. It's very important. Don't forget about any about this one. But it does carry, I mean, you literally pick up like where we left off. I wish we could do chapter 12 by Mr. 1 as well, like I used to, but maybe shorten the semester. So I haven't been able to do that last time. Okay. The picture at the top just shows you like a little cartoon of some of the possible ways that this can happen. And then I'll talk about like caveolin and clathrin in a moment. Okay, so what happens here is one thing that they've noticed, depending upon the membrane type, sometimes you can get this accumulation of cholesterol that's higher in that localized area, so it becomes much more rigid. You remember that's the functionality, or that's a biophysical property of cholesterol, I should say, not functionality. It's a property of cholesterol. And then there could be proteins that become more associated, or they get turned on or activated based off of what other protein comes together inside that raft, or based off of what either external signal or secondary messenger that comes that activates the protein or proteins that are involved in that raft, that microdomain. Okay. This is, I don't know why I put this in here. Oh, I think this was just a little bit, just as a review. Really, this should be a review of different ways of, different types of activities that can happen there along the membrane. And so, for example, which I don't know, I'm assuming you guys cover the Golgi apparatus and Cell-Molec, but one thing that you can have is that the Golgi apparatus, which kind of looks like the little flapjacks, but they do bud off, and so you can have exocytosis to where then, and we'll talk a little bit about that in a moment, but where you can have the membrane of the vesicles merge with the membrane of the actual plasma membrane in order for it to dump its components. Likewise, you can actually have endocytosis. And we'll talk a little bit about the roles of caveolin and clathrin with respect to endocytosis in just a moment. But another thing that can happen, of course, there's viral infections. Depending upon the virus, they utilize different machineries and can. So, for example, I don't remember in this class, did I talk about hemagglutinin? So I used to always talk about hemagglutinin for influenza virus. It's really, really cool, okay? So, no, it's bad cool, I guess. So the way that if you ever hear about, whenever they talk about the virulence of the influenza virus, or they just say what kind of influenza virus is happening that year, what do they say? Does anyone know, like, what's a bad strain of influenza virus? And don't tell me Spanish flu. Give me specifically, like one that has a scientific term. Like H1N1. Well, the H stands for, so the influenza virus only codes for itself, I want to say it's 3 proteins. I may be off on that one. It has the H, which is hemagglutinin, N, which is a neuraminidase, and a C, which is a capsid protein. It may have more as well, but it has a very limited genome. But the H is a hemagglutinin, and based off of that, the isoform of hemagglutinin, it's what is used to cause the virus to merge. And so it is probably one of the best examples of protein movement within the same protein. Whenever it goes to infect a cell, it is really, really long. It's huge. And it kind of looks like hands, actually, where one side is stuck in the membrane of the virion, and then the other side reaches out and it recognizes some of the proteins on the cell that's going to invade. And whenever it clasps and grabs that, it gets activated and it brings the two together. So the two hands actually come together in this site. I used to know the exact number from the crystal structure, but I don't remember now. I had no about physics. But it's a huge movement. And that's actually what comes together. It causes the membranes to come in close proximity where they can merge and the virion can dump its viral particles. That's what it's trying to show there. And of course, we can have fusion between sperm and egg. I'm not going to discuss vacuoles. Okay. So, this is just another example. We actually go over this, even though I'm sure that you're going to forget. Please don't, I'm sure you will. We're going to go over this in great detail next semester when we talk about cholesterol. But this is just an example to show how endocytosis and exocytosis, for that matter, how it works and goes together. This is specifically for cholesterol. And remember, cholesterol is actually not typically transported in your body in the form of cholesterol. They're transported as cholesterol esters, okay, which that's actually not shown, and there's one in more detail that we go over next semester. But the LDL actually encapsulates with the cholesterol esters. And so what happens here is whenever the LDL binds onto its membrane receptor, it's going to activate typically a microdomain or activate some type of proteins, and it changes the localized structure of that membrane. Okay, so these membrane receptors usually are oligometric, but it causes some type of activity within the cell. Okay, so what happens here is, I think with LDL it's clathrin, not caveolin. It's clathrin that gets recruited, and we'll look at an example of it in just a moment. But the shape of the proteins causes the shape of the membrane. You know, you can imagine you have those proteins kind of concave. As more and more of them come together in the same region, it's going to make that region of the membrane also concave. I'll show you an example by me in just a moment. And literally it'll pinch it off. So then the vesicle gets transported and the pH will change. And they'll ultimately be degraded, the vesicle will, and so the cholesterol will be dumped out. You can actually recycle the LDL receptor. That's what it's trying to show over here. Just a little side note, this is a part that is different about it versus a lot of other receptors, and we go over in great detail next semester, and this is the part that I say that people typically forget. To me, whenever I was learning about this, it always seemed counterintuitive. Let's say that you eat a really, really heavy diet. So you have those french fries from McDonald's or what have you. And so you got a much higher concentration of exogenous cholesterol. Okay? So what happens is once the cellular level, whether it's endogenous or exogenous, cholesterol reaches a certain amount, it actually inhibits the synthesis of its own receptors. Because this cell, and that would seem contrary. Whenever I first started thinking about it, whenever I was a student, I thought, if you have cholesterol, you're going to want it to come, to get it out, right? Out of your extracellular, out of your body in general. Well, so what happens is this cell is saying, I have enough, I don't need any more, and so I'm not going to make any more receptors. So then your cholesterol is going to build up outside that cell and have to go to other places. Okay? And so it's one of the examples of where it actually turns off its own receptor. I haven't clicked on the picture to see if the movie, I always show the movie next semester, because it's like a 6th grade class that acts this out, and so it's so corny, but it still is awesome. Okay, so here's some examples. This is using the protein caveolin. So caveolin, whenever two of them come to form a dimer, they force that curvature. There's another protein called clathrin that I mentioned, and clathrin is very similar in that sense. That clathrin already has an intrinsic structure, and so by more and more clathrins coming, in fact they call them clathrin-coated pits. Back when you may talk about that in some molecular biology. These regions that are like invaginated, or become invaginated because the clathrin coats it on the inside, and the clathrin already is shaped a certain way, so we call them clathrin-coated pits. But you can actually see where the invagination is starting to occur there. Okay. Oh, whoops, I forgot that I actually blew these all up. So there's a blow up of what I've been talking about. And then we can see how the caveolae form by the dimer formation of caveolin. Okay. All right. Now, some of the ways that we get this to happen, in the way that the membrane can change its shape, is due to an intrinsic protein structure. And so you can imagine now we have this peripheral protein, and it's got a specific shape. And so whenever it binds to the membrane, it will force that membrane, which is relatively fluid, to take on that, whatever that shape may be. Okay. Or we can have an oligomerization to occur. So now we have the region that we have these monomers that come together to form some type of, superstructure, that's a better word than mine, that's what we come up with, that's going to cause the formation, the membrane to either be concave or convex, depending upon which direction you're talking about. Okay. Another possibility is you can actually have an amphipathic protein. And so it literally, to me, looks like a spaceship. Maybe it was about X-Files coming back on. But the fact it inserts itself in that membrane, so it will force that membrane to take on that specific structure. All right. Now we're going to talk about the snares. And I've got each of these blown up on the subsequent slides. This way you can see the entire process, and then we'll take us through, just because sometimes I've taught in classes that were really hard to see. So the snare process, there are snares and there are snaps. Okay. And I don't remember, I want to say they were getting cutesy at some point in time on like what snap and snare meant something, but I don't remember now. That's not the important part. Okay. So let's say that we have an outside vesicle, for example, and the vesicles are not the only ones that can utilize something like a snare, this kind of process here. But this is just showing an example with a neurotransmitter. So what happens is it has a vesicular snare on it, the V snare, and then it recognizes the incoming T snare of the cell that it wants to invade, for lack of a better word. Okay. So whenever they come together, they form these interactions between the two proteins, or sets of proteins actually, and they really do kind of look like a zipper. Okay, so where they form these really tight interactions between the different proteins, and there's a conformational change, which is not obvious here. There's a conformational change that's going to occur, similar to what I was talking about with the hemagglutinin, that's going to literally bring the two sets of membranes closer together. Okay. Also, whenever they come together, it's going to force a curvature upon that membrane. Okay. So the first part is called hemifusion, or half, as you can see depicted here in the bottom, to where the two outer leaflets get fused together. Okay. Then the hemifusion, and the inner leaflets will be coming, and you get what may not be even more interactions between the two snares as they kind of zip up like little zippers as you go along. And then you have the complete fusion. Now we're going to be able to have a little pore, and the neurotransmitter gets dumped into the postsynaptic cell, or the cell that it's supposed to go to. Okay. Any questions on snares and snaps? Snap is just the one that's on the internal portion, kind of helps hold the snares into place for the snapping process, I guess.
So those are proteins?
Yeah, those are proteins. Those are all proteins that recognize each other.
V just stands for vesicle and T stands for...
I don't remember what T stands for. Vesicular, and I have to look it up.
So do they get recycled after this?
I don't know. I don't know in this instance here where we get recycling. Usually you get something so extensive many times. Recycling is meant that meaning unzipping. Many times, sometimes the way they can be recycled would be they get degraded, right? And then you recycle the amino acids. But yeah, in this one in particular, if you have something so extensive, you can imagine it's going to be a lot more difficult for it to completely come apart. The reason why is the next All right. Our subject matter actually should be review, but I actually like to spend a little bit more time on it. And I will do it real quick. Just for this one, and then we'll talk over facilitated versus passive diffusion and active, passive, facilitated diffusion, all that kind of stuff on Wednesday. Because it too should be pretty much a review. And then I'll give like a real case study of like microdomains and wraps. Okay, and so here this is just different types of the different types of transporters or diffusion that can happen. And so if I want to do a quick review of these, we have simple diffusion, okay, which is literally where the substrate goes from the outside to the inside. Typically these are going to be nonpolar, right? They're usually going to be small. Or we can have facilitated, where it goes down the gradient from the outside to inside or vice versa. Okay, you can have a primary active transport where you go against a gradient. Please note it's going to acquire some type of energy. Usually when we talk about energy here, we're talking about the hydrolysis of ATP. Then we can have a secondary, which is this one is called an antiporter. Nope, I lied. That one's not the antiporter. They didn't show an antiporter on this one. It can be. Antiporter means they go against each other, or they can be a symporter. This one actually doesn't show anything. The symporter means they go in the same direction. Antiporter means the two things are going in opposite directions. We can have an ion channel, and then we can actually have an ionophore, okay, which one example of an ionophore is like something like it's called by like lincomycin or something. There's some drug treatments that cause these. We'll go over some ionophores in next semester with mitochondria in particular. Okay. So it's like a 1-minute spiel on the different types that we'll cover in greater detail on Wednesday. Are there any questions? Anything? I don't want to go and show you like graphs and stuff and have to go over that in like 30 seconds. So on Wednesday, we'll go over the different, into more detail, the different types of diffusion. And like I said, we'll also talk a little bit more about some of the more recent developments. I'll give at least one example of microdomains and how that they play a role in vivo in the disease state.